So previous lecture, you know what is the linear transformation, what is the linear mapping. Now we are going to talk about the kernel of a mapping. Kernel of a linear map. So what is the kernel of the linear map uh, is saying. So suppose T is a transformation from one vector space V to another vector space U. Okay, so T is a transformation from one vector space to another vector space U. Okay, and U and V, these two vector spaces defined over the same field F. Okay, in the this vector space there is some vectors, right? Now, what is the kernel of linear map? Is saying that. Okay, so before that, as V is a vector space, so there is some zero element theta, and similarly U also has a zero element, let's say theta dash. Now, as T is a linear map, so we already shown in the last lecture that uh, theta, the zero element of V, always map to that zero element of U. The kernel of a linear map is that all those vectors in V in this set that maps to that zero element of U. So suppose there is another element that is also mapping to that theta naught, that is zero element of U. So let's write this is some U1. That there is another element, let's say, that is also mapping to theta naught. Okay. So set of all those vectors in V which are basically mapping the zero element of U is called the kernel of a linear map. Okay, so let's write the definition. Let V and U be two vector spaces, right? Over the same field F, and let V to U be a linear mapping, be a linear map or linear transformation, then the set of all vectors of V which maps to the zero element or zero vector of U is said to be kernel of the map. So therefore, KT basically is equal to, this is called R, KT is the set of all V in V such that T of V is mapped to the zero element of U, right? So theta is the zero element, so theta naught is the zero element of U. Now let's us find the kernel of some linear transformation. So first example, find the kernel of the transformation T, that is mapping from R cube to R square, defined by T of xyz is equal to x plus 2y plus 3z, comma x plus 3y plus 2z and xyz is belongs to R cube. Okay. Now we have to find that kernel of the transformation. Okay. So let's solve this one. So let some vector, let's say u, that is equal to xyz, belongs to kernel. Okay. Then by the definition of the kernel, u will be mapped to the zero element of R square. And what is the zero element of R square? That is 0 0, right? Therefore T of u, and u is equal to xyz, so therefore this implies T of xyz is equal to 0 0, right? Now T of xyz, that is equal to x plus 2y plus 3z, comma x plus 3y plus 2z, this is equal to 0 0. Now if you compare these two coordinates, then you will get x plus 2y plus 3z equal to 0 and x plus 3y plus 2z equal to 0. Now here we have to find xyz, all the solution of that xyz. Now you see, this is three variable, three unknown, and two equations. Therefore this system has infinite many solutions. Now we solve this equation. Okay, so what we can do is by subtract number 1 equation to number 2, then we get x will get cancelled. So here 2y minus 3y, so minus y, and here 3z minus 2y 2z, so that is plus z. This is equal to 0. So this implies y equal to z, right? Now if you put y equal to z or z equal to y in that equation 1, then from 1 by substituting y equal to z, you will get x equal to minus 5z, right? So therefore all the solution of the system of equation xyz, this will be of this form: k into some x is minus 5, right, and y is 1 and z equal to 1, right? So this is for k belongs to R. Therefore cot T is basically that all that linear combination of this vector, minus 5, 1 and 1. So this is our cot T. Okay. Now there is another definition that is called the nullity of the linear transformation. What is that thing? Suppose we have a linear mapping from one vector space to another, and we can find a cut T by that previous method. Okay, right? Now you find out the cut T of that linear transform. Suppose T is a linear transformation from V to U, then you can find the cut T. Right? You can find the cut T, that set of all the vectors in D such that V of D is that zero element of U, right? So you can find the cut T. Now dimension of this cut T, that will basically will be the nullity of T. Okay, so dimension you can find out, right? Now if you take the previous example of this one, okay, so here we find out ultimately the cut T here, that is equal to linear span of this vector. Now here this cut T is generated by only this vector, right? Therefore the dimension of the cut T will be 1, right, because it is generated by only one vector. Therefore nullity of T will be 1, right? That is the dimension of cut T. Now we'll just state some theorem. Okay, so we can use that theorem in our problem, the various problem. So theorem, first one is that suppose we have two vector spaces V and Q, two vector spaces, okay, two vector spaces over the same field A. Okay, so these are two vector spaces. Then uh, the linear transformation, let T be a linear transformation from V to U. Okay, this is a linear transformation or linear map. Then cut T is a subspace. Cut T is a subspace of V. Okay, so cut T will form a subspace of V. Okay. So subspace, you know how to find if the two elements are you take in the cut T, if their addition are there and scalar multiplication with a vector is present in the cut T, then the cut T will form a subspace. Okay. Now second theorem that will state without proving. So here, given that T is a linear transformation like the previous one, so T is a linear transformation from V to U. Okay, the linear, so linear map, and uh, then T is 1 to 1 if and only if cut is only the zero element of cut is theta. Okay, so T will be 1 to 1 if cut T contains only zero element. Now we state another theorem without proving, that it's saying that suppose T is a linear map from P to U, a linear. Okay, now also given that cot t is theta. Okay, cot t is only contain the theta. So t is 1 1 by the previous theorem, right? Then any linearly independent set of V will be linear independent in U. Okay. So what I'm saying that, so suppose from this V, if you take, let's say, U1, U2 to UN be linear independent, okay, Li linear independent in V, then that if you take the map of individual all the elements U1, U2, UN, so then this set T of U1, T of U2 to T of UN, so this one will be linearly independent in U, okay, in the codomain. Now let's search to one problem of the linear transformation. So here one transformation is given. We will find what is the cardinal set or card set of this transformation. Okay. So given that uh, uh, that T is a transformation from R cube to R square, and it is defined in this way: T of x y z is mapped to x plus y, x minus z. Okay, then find the cut t and dimension of t. So let's solve this one. Dimension of not t, dimension of cut t, or let's say, so dimension of cut t is also known as nullity of t, right? So T one mapping is given, we have to find what is the cut T and the dimension of cut T. Okay. So let's say that U be any element of cut T, let U equal to x, y, z is belongs to cut T. Then T of U will be equal to the zero element of the codomain, that is 0 0. Right? So T of U, that is equal to T of x, y, z, this is equal to 0 0. By the definition of the transformation, we can write that T of x, y, z, this is equal to x plus y comma x minus z. Right? So we can write is x plus y comma x minus z, that is 0 0. Now by comparing two sides, we will get x plus y equal to 0 and x minus z equal to 0. Now we solve this system of equation. Now here is also 3 unknown and 2 equations. So there is infinite many solutions. From this equation, you can write x equal to y, right? Or y equal to z, so better to write y equal to z. So it's right y equal to minus z, y equal to minus x. And from next equation, from this one, you can write z equal to x. So x, y, z, any element of this part t, you can write as x, and y is minus x, and z is x. Right? So if you take common, so it get 1 minus 1, 1. So the part t will be linear span of this vector, right? 1 minus 1, 1. So cut T is generated by this element. Now this only one element, that is the non-zero. Therefore nullity of T, that is 1, right? Dimension of cut T.